Hi everyone, my name's Stephen Bennett. I'm in Kim Jelf's group at Imperial College London, and today I'm going to give a talk on my research on the discovery of synthesisable materials. So my research is kind of a hybrid between computational and experimental, and today I'm going to be talking about how we kind of applied computation to do a high-throughput screening for synthesisable materials, and how it was possible to synthesise those in the lab as well. So my research is targeted towards the discovery of porous organic cages, and these are a subclass of porous molecular material. And they're typically synthesized using kind of reversible dynamic covalent chemistry reactions, such as imine condensation. And these typically lead to, due to the thermodynamic mechanism, like error correction, and often form like these complex, diverse topologies. These cages can form these diverse topologies, which give rise to this central internal cavity, and then this makes them useful for applications in porous materials. So typical applications for cages include gas storage, molecular separations, and also catalysis as well, and these all originate from this permanent internal cavity. They also offer advantages over kind of conventional porous materials such as zeolites. Due to their organic nature, this makes them kind of solution processable, and this allows for post-synthetic modifications, which could dramatically lead to an alteration in the properties as well. And as the demand is kind of increasing to tackle global challenges such as climate change, we're increasingly looking towards these alternate sources of material for these applications. So cage discovery is challenging, and despite there being almost infinite combinations of precursors that can be combined due to their organic nature, it's still rare to discover a cage. And this is kind of exemplified between 2009 to 2017, in which less than 10 cages were discovered per year. However, this is starting to increase from 2018 with the rise of automation, and significantly many more cages have been discovered in this year, as we can now kind of systematically combine these precursors together in a kind of almost autonomous way now. So I'm going to talk a little bit now about the challenge of organic materials design and kind of the process that a chemist might take when designing a new material. So firstly, the initial step is the component availability. So which precursors can we target that are synthetically accessible within a few reaction steps, or are commercially available for cheap commercial cost? However, we must then ask the question of whether those precursors will give rise to the actual desired properties that we want in the material as well. And so following this kind of precursor selection step, we must then ask the question, will the desired material form from these selected precursors? And for cages in particular, this can be quite challenging because it could result in not these kind of unique topologies, but kind of a mixture or even a polymer output, depending on what precursor we combine. And finally, there's the formulation step as well. So once we finally synthesize this material, can we process this material into its final kind of structure, and will it maintain these properties in this form? So in my talk, I'm going to be focusing primarily on the component availability, and can we predict precursors that are synthetically accessible and will form a shape-persistent cage? And so computation can help address many of these challenges, and it can be applied in kind of a high-throughput manner to help screen many thousands of possible candidates nowadays. And so in my talk, I'm going to be discussing how it's possible to kind of screen for synthetic accessibility prior to going into the lab and actually synthesizing these materials. So there are a variety of ways in which we can predict the synthetic accessibility of a molecule. So firstly, we can kind of look at the structural complexity. Complexity can be a function of stereocenters, macrocycles, heteroatoms in a molecule, and all these can deem a molecule as more complex and therefore kind of more difficult to synthesize. Next, we can kind of quantify the position a molecule is likely to lie in a reaction pathway. So molecules more likely to lie towards the end of a reaction pathway could be deemed more synthetically inaccessible, and these are typically achieved using kind of more data-driven approaches. Thirdly, we can kind of model the chemist intuition and model their decision-making process that they may take when selecting a precursor, and use statistical methods to try and identify these kind of biases towards different precursors. Or finally, we can use retrosynthesis planning, which aims to kind of identify a plausible reaction pathway to commercially available compounds. And so while each of these approaches can give kind of a value for synthetic accessibility, on their own they aren't particularly accurate. But when kind of combined together, they can be useful heuristics to help bias towards more easy-to-synthesize precursors and help disregard the most difficult to synthesize precursors. So we can help target both our computational and experimental time towards more synthetically achievable precursors. So we set about trying to create our own model based on Chemist Intuition. So we rephrased synthetic accessibility as a binary classification problem. And we sent our collaborator over 10,000 molecules and asked them the question, can you make 1 gram of this compound in under 5 steps? And so we compared our chemist training data also with 2 open source measures of synthetic accessibility, the SA score, which is a measure of complexity, and the SC score, which is a kind of a quantification of the likely position a molecule is to be in a reaction pathway. And we found that these scores weren't able to kind of replicate our training data. So kind of meant that we would have to design this new model in order to tailor it towards our specific problem. So we set about trying to differentiate between easy to synthesize and difficult to synthesize precursors. And for this, we chose a random forest model based on the number of data points that we had, which was 12,553 scored, and also their popularity in other cheminformatics problems and relative ease in which they can be implemented, and also the few hyperparameters that we had to optimize as well. So we found that our model was able to achieve relatively high accuracy of 88%. However, we obtained quite an imbalanced data set with many more difficult to synthesize molecules than easy to synthesize. So instead of focusing on accuracy, we instead focused on the precision of our model, and we tried to minimize the number of false positives that we obtained. And in our case, a false positive would mean that a difficult to synthesize molecule would instead be classified as easy to synthesize. And so if sent to a collaborator, would end up wasting their time and experimental efforts. And we chose this kind of trade-off because chemical space is very, very large. So despite having a relatively poor recall, and we're missing quite a few easy to synthesize molecules, because chemical space is almost infinite, this was a trade-off we were kind of happy to make with our model. So once we had this model, we then set about applying it towards a high-throughput screening workflow for porous organic cages that aimed to kind of identify computationally shape-persistent cages without any human input. So initially, we prepared our precursor database, and we used the model that we generated, in addition to the SA score and SC score, to remove the 99% of the most difficult to synthesize precursors, leaving only the 1% easiest to synthesize. And then we built our cages using a software package developed in the group, the Supramolecular Toolkit, or STK. And so STK builds these cages by placing precursors on predefined vertices corresponding to a cage topology, and kind of cheminformatically building the bonds between them based on the kind of the dynamic covalent chemistry reaction you're trying to create. And so in this workflow, we focused solely on diamines and trialdehydes and a single topology. And despite limiting ourselves to only these three factors, because there are so many different combinations, we ended up screening 28,185 different precursor combinations. And so once we'd built the cages in STK, we then performed a molecular dynamics conformer search to help identify the lowest energy conformer, and which will hopefully give a representation of whether that cage was likely to maintain that permanent internal cavity in the gas phase. And then we assessed whether it maintained this permanent internal cavity using our in-house software package PyWindow. PyWindow aims to detect internal cavities and windows by applying a sphere of sampling points to the internal cavity, and it can be done in a relatively high throughput manner, so allowed us to quickly screen all of these possible cages. And both of these codes are all open access on the group's website as well. So promisingly, once we'd finished this screening workflow, we found hundreds of cages that were predicted to be shape-persistent following the optimization process. And this is a great many more that have been experimentally realized to date, and it's promising that there are also many more to discover in the future as well. And we found that many of these cages had a cavity diameter of around 5 angstroms, which is a value typically found in the literature. We're also promisingly able to identify some larger cages as well, including those with a cavity size of greater than 16 angstroms as well, which can be seen on the right-hand side. And while it wasn't the direct goal of our model, we also found that our model was more likely to select precursor combinations that favored the formation of shape-persistent cages compared with the SE score and the SA score, and also a randomly selected control sample as well. And this suggests that our model could be relatively useful for experimental chemists when designing cages, as it not only was able to predict kind of easy-to-synthesize precursors and bias towards those, but also cages with a shape-persistent, precursors that were more likely to form a cage with a shape-persistent cavity also. And so from this model, we were then able to identify this transalkene trialdehyde precursor that was present in 6 of the 7 of the largest shape-persistent cages as well. And we're able to synthesize this in 2 reaction steps, which is based on kind of simple reaction chemistry and was relatively easy to synthesize in a higher yield. And so despite our model being able to now predict easy-to-synthesize cages as well, it's also challenging to predict computationally whether this topology will actually form and whether this precursor will form a cage or a mixture of topologies or a polymer as well. And so to help address this problem, we're using combinatorial searches, using kind of high-throughput automated methods to explore combinations of this trialdehyde with various diamines to help generate a data set to create a data set with the goal of predicting cage formation and reaction outcome as well. And so using the OpenTron's reaction platform to systematically combine diamine and trialdehyde precursors, we're in the process of creating an experimental data set. However, predicting cage formation is quite a challenging task owing to using conventional computational methods, owing to the difficulty in modeling each possible reaction outcome. So instead, we're going to focus on using more data-driven techniques to help identify the possible reaction outcome and help generate a model that can address some of these computational challenges. So I'm just going to conclude now with these final points. So computational screening can help bias towards easier to synthesize molecules when combined with chemist intuition. However, kind of on their own, these scores cannot accurately predict whether a molecule is easy to synthesize, but can bias towards more easy to synthesize precursors in a high-throughput screening workflow and can help disregard difficult to synthesize molecules. Many of these scores disagree on what defines synthetic accessibility, and so, cannot be used on their own. But it was also promising that from this high-throughput screening work, many shape-persistent cages can be made even when restricting our initial data set to only the most easy-to-synthesize precursors, including those with a large cavity size as well, which is a property kind of not typically identified in the literature as well. Cool, and with that, I'd just like to finish off by acknowledging everyone in my group and my collaborator, Rebecca Greenaway, who's providing me with the opportunity to synthesize some of these cages that I predicted computationally. And I'd also like to thank the Leave Hume Trust as well for my funding. And I'd like to thank you all for listening as well.